Now, there's more to this than what I've shared with you. We're going to talk, if you take AP with me next year, we're going to do a little bit more of that. It's not a lot more, but it's just a couple little things that we have to cover. But we talked about this electron geometry and the shapes that made, and how we had those different domains. And you guys built those yesterday. Today, we're going to talk about polarity. What is a pole? North Pole, South Pole, magnets, what is it?
And then attracting?
Well, sometimes you have attractions with it, yeah, but it's two different sides, right? Like a North Pole versus a South Pole. When we're talking about in terms of atoms, though, we're not talking north and south. We're talking positive and negative. Okay? Now, there's two different types of polarity that we need to discuss. The first one is called bond polarity. And this is where you're looking at the electronegativities. And again, like I will give you a chart if you need it for your test. I need to do that. I ran off the test today and I didn't run that off with it. I need to write that down. All right. So like I said, when you do this, you're going to end up looking at the electronegativity differences. Okay. When those electronegativity differences are the same, then you have a nonpolar bond. When they are different, you have a polar bond. So when you are looking at, for example, carbon and hydrogen, carbon is here. It is 2.5. Hydrogen is 2.1. So the electronegativity difference there is 0.4. That means that this is going to be a polar bond. How do I know that? Well, when in terms of differences here, anything that's 0 to 0.4 is going to be considered a non-polar bond in terms of differences. Anything that is 0.4 to 1.67 is going to be a polar covalent bond. So they're still going to be sharing electrons. What? What question? And anything that's greater than 1.67 is going to be an ionic bond. Now, the closer you get to this, the more the properties will start to act more like an ionic compound. Now, what does this even mean? Like, why does this matter? What does this mean? Well, if you're talking about a bond between hydrogen and carbon, okay, remember what electronegativity is. Electronegativity is it wanting those electrons to stay by it more than the other thing. Okay, so by carbon being more electronegative than hydrogen, the electrons are going to stay on this side of that bond around the carbon a little more. It's going to be drawn to the carbon more than the hydrogen. Because of that, when you have that, you typically have this being a negative side and this being a positive side. Is that making sense?
I missed the start of that. So you said something would be more attracted to carbon.
The electrons.
Presumably, which one's the positive? Oh, the electrons. Negative.
This would be your positive side. This would be your negative side.
Because carbon is more electronegative than hydrogen.
Yep, because carbon is more electronegative than hydrogen. This side's going to be more negative than this side. That creates a pole. All right. Now, that happens in terms of these, just when we're talking about bonds. Okay. If we're talking about something like H and F here, look at the electronegativity difference between that. This is 4.0 minus 2.1. That comes in as 1.9. So that is very, very polar. Your electrons are going to be over on this side way more than they're going to be over here.
What are you subtracting?
What?
What are you subtracting?
The electronegativities. So in the chart here, you have your fluorine, and you have your hydrogen. And you subtract those electronegativities and you look at the differences. All right. Now, that has to do with bonds. So you can look at these bonds and see that. But there's another factor that comes into play, and that deals with the molecule itself. Okay. So, and this is where it gets a little... What you have to do is you have to look at the molecule to see how it's divided out in those 3 dimensions. Okay. So when you're talking about any substance, okay, any molecule, the first thing that you're going to want to do is you're going to want to look at that central atom. If your central atom has a lone pair of electrons, at least one lone pair attached to it, it is always polar. So one or more lone pairs of electrons on the central atom equals always polar. So you don't even need to, if you see this here, if you see this, just write down polar, you're done. You don't need to think anymore. Okay? So if there is a lone pair of electrons on that central atom, write down polar, drop the mic, walk away. Okay? Now, what was I going to say next? Polar. Okay, how do we denote that? Okay, that's what I was going to show you. There's a couple ways that you can show that polarity to the person that you're trying to indicate this to. Way number 1, you draw an arrow towards the negative end, and the other end you put a plus sign on. Okay, so if we're looking at this, let me draw that again over here. If we're looking at this, we would draw an arrow towards the negative end, and then the other end of the arrow, we're going to make a plus sign. Good. The other way that you can do it, what? Okay. The other way that you can do it is you can use this funky looking Greek symbol. It's like an S with a kind of curly Q on the end, and you do a negative at the one end and the positive at the positive end of it. Okay. Now, sorry, you guys. One thing that you have to kind of be aware of with this is if you are dealing with something like, let me see, chlorine 3, 2, yeah. Okay. If you're dealing with something like this, okay, so carbon tetrachloride, it's going to be drawn like this. Okay. Now, this has bonds here that are going to be polar bonds, because if we look at the electronegativity difference here, chlorine is a 3 and hydrogen is a 2.1. So that gives us a difference of, right, which gives us clearly a polar bond. Okay. But here's the but. This is symmetrical. And that difference is played out equally around the entire molecule. So even though you have polar bonds, this symmetry of this is going to give you a non-polar molecule. And that's the kicker.
So even if the bonds are polar, if the molecule is symmetrical, then the molecule is non-polar.
Correct. And remember, if you have lone pairs of electrons on that central atom, it's not going to be symmetrical. The lone pairs of electrons on that central atom override that. Drop the mic, walk away. It is going to be polar all day, every day. Don't even have to think about it. Now, let's look at something like this, because this is where and I don't know if I wrote that. I probably didn't write that in the right order. Okay. If I draw this out, this appears to be symmetrical, yes? But if you think of this in terms of electron geometries, okay, so I'm going to kind of redraw this. Think about how many electrons chlorine has. How many? 17. Chlorine is sitting here like this, 17 electrons, and hydrogen has its 1. Okay. Do you see all of a sudden where you've got a huge concentration of electrons on one side versus the other? This is going to be a polar molecule and look like that, where this has that concentration of electrons. It's not going to be symmetrical like this guy is. See how this guy would be all spread out even, nice and pretty? Here, that's not happening. I know. You got to wrap. You got to wrap your brain around it. You got to do some practice, okay? I get it. All right, we're going to look at this guy. We've got CH3OH. So I've got my carbon here. I've got my 3 hydrogens. I've got, remember, if we have an oxygen and an H beside it, that oxygen is going to be connected to the carbon. Okay. Now we need to count up our electrons. I got 4 plus 3 plus 6 plus 1. So that is 10. I've got 14, right? Am I doing my math right?
Yes.
So 14 electrons I got to spread out here. I got 2, 4, 6, 8, 10, 12, 14. Okay, so I got my thing.
Oh, you're right.
2, 4, 6, 8, 10, 12, 14. Now, they wanted this drawn in 3 dimensions. I'm not so good about that. So you guys can practice on that if you want. Molecular geometry around the carbon. So here we have two things that could potentially be our central atom. They have to tell you which one you want to look at. Okay. So you are looking at the carbon. They have specified the carbon. So you are looking at the geometry around here. Okay. So you have a central atom with four things connected to it. What is the geometry when you have a central atom and four things connected to it? Four atoms. Yep. Merrick? Tetrahedral. Yeah. Okay. Now, they want us to turn our focus onto the oxygen this time. Okay, so now we're looking at the geometry of the oxygen. So here we have two atoms and two lone pairs of electrons. What geometry is that called? Bent, right. Okay. Now, we essentially have two central atoms here. And if either one of them has a lone pair of electrons, we have a polar molecule. So this oxygen right here has lone pairs of electrons. That means that this is going to be a polar molecule. All right, let's look at CO2. I'm going to draw my carbon here, and I've got my oxygens connected to it. My carbon has 4. I have 2 oxygens times 6 is 12. So I have 16 electrons that I need to spread out here. Right now I have 4, 6, 8, 10, 12, 14, 16. What problem do I have? Carbon only has 8 or 6. It needs, carbon only has 4. It needs 8. So I am going to try and erase these, and I'm going to bring them in and make double bonds. Now everything has 8. What is the geometry around here? I have 2 atoms attached to a central. No lone pairs. Linear, correct. Okay. And now they want to ask, is it polar or not? Are there any lone pairs of electrons on the central atom? No. So that's the easy way to figure this. Okay. Are both of these the same atom, and so it's all going to balance out? Yes. So this is nonpolar. Yep.
But now whoever gets everything for the balance out.
What, hon?
You said everything going to balance out, which is why.
Right. Because if you look at the electronegativity difference between the bonds, this is 2.5 and this is 3.5. So there's an electronegativity difference of 1 here, which means that these are polar bonds. So the bonds are polar, but because everything is in balance, it's in symmetry here, then it's a nonpolar molecule. All right, we are going to sketch this guy. We have C, which is 4, but we've got 2 of them, so that's 8. We have hydrogen, which has 1, but we've got 4 of them, so that's 4. We have a total of 12 electrons that we need to arrange. I'm going to put my carbons in the middle here and connect them. I'm then going to connect a hydrogen to each one of these. Okay. Now I need to figure out a way to get this to balance out. Right now, out of my 12, I have used up 2, 4, 6, 8, 10. And I need to use up 12. So I need 2 more. I could put it here, but then this wouldn't have enough electrons. So what do I do?
Double bond it.
Double bond. Okay. So now, and this is the exact problem that was on my AP test yesterday. And so many of them got this wrong. I only had like 2 people in a whole class that got this right. Let's see if you guys can do it. You're looking at one of the carbons. So we're going to call this carbon 1 here, and this carbon 2. Okay. You have this carbon. It has 1, 2, 3 atoms attached to it, and no lone pairs of electrons. What would it be? Trigonal.
Yes, that one.
Trigonal what? You have planar and pyramidal. Planar. Very good. And what is its bond angle? This is what they missed. 120. That's all they had to do. Uh-huh. Yep. It's as easy as that. They're going to kick themselves. Well, this isn't hard. The 120 isn't hard because you've got, if you think about a circle, right? If you think about a circle and you divide that into thirds, right? Well, the circle is 360. So if you divide 360 by 3, it's 120. So that's really the easiest angle to memorize. That and then the 180. Like up here, this was linear. With this linear, that's 180 degrees. That's all in one straight line. I think that's pretty easy to remember too.
How did you figure out the angles?
Well, it's on your chart.
On the chart, that's all.
So you can, if you,
Like on this.
on your notes chart.
Oh.
But again, if you just apply simple geometry to this, if you have a circle that has 360 degrees and you're dividing it into thirds, the angles are going to be 120. All right. And then the angle around this second carbon is going to be the same. It's going to be the same geometry. Polarity here. Is this in symmetry? Yep. So this is nonpolar. All right. So you guys have the rest of this assignment and your review, which I'm going to pass out to you. All of that is going to be due on Monday.